Alright, so this is section 1.8, new functions from old. This section is basically about creating new functions by composing, stretching, and shifting functions. The book starts out with an example of a composite function, or a function inside another function. The example the book gives is a drop of water falls onto a paper towel. The circular damp spot's radius grows as a function of time. In other words, every second, we'll say, that goes by, the radius expands. So we have two functions, f of r, which is equal to pi r squared, which is the area of the circular damp spot, and we have g of t, which is equal to t plus 1, to show the time that goes by. So now let's say we want to know how big the spot will be 3 seconds after this drop hits the towel. So we plug 3 into f of g of t. The first thing we do is we plug 3 into g of t, giving us 4. We then plug the number 4 into f of t, which gives us 16 pi. So this means that 3 seconds after the drop hit the towel, the damp spot has an area of 16 pi. So basically, what you're doing is you're calculating the inside function first, then calculating the outside function using the answer from the first function. The next part of section 1.8 is stretches of graphs. This section mainly deals with the stretching and flipping of graphs. There are 3 ways shown to do this in this section. The first is stretching. So we'll look at the graph f of x equals x squared. Now, to stretch it, we will multiply the function by a number larger than 1. We will use the number 2 to create the graph y equals 2f of x. This is basically saying that we are multiplying every value in the function f of x by 2. As you can see by the two graphs, the graph y equals 2 times f of x is slightly longer and more elongated than f of x equals x squared, thus stretching it. This happens because by multiplying the graph of f of x by 2, we are doubling the values of y, making the graph grow faster. The next thing shown is the shrinking of graphs. This is done by multiplying a function by a number bigger than 0 but smaller than 1. So again, we will use the function f of x equals x squared, and to shrink it, we will multiply it by 1/2. As you can see, the graph of y equals 1/2 f of x is smaller and takes longer to grow than f of x equals x squared. This is because we are halving the y values and making the graph grow at half the rate. The last part of this section involves the shifting of graphs. This can be done 2 ways. The first way is moving the graph. The last part of this section involves the shifting of graphs. This can be done 2 ways. The first way is moving the graph horizontally. This is done by adding or subtracting a number from x. For this, we will use f of x equals x squared and g of x equals x minus 3 squared. As you can see, subtracting 3 from x has shifted the graph to the right. If one were to add 3 to x, the graph would have shifted to the left. The second way to shift the graph is vertically. This is done by adding or subtracting a number from, in this case, x squared. For this example, we will use f of x is equal to x squared again, and f of x is equal to x squared plus 3. As you can see, adding 3 to x squared has shifted the graph up 3 spots. If one were to subtract 3, it would have moved down 3. Alright, well this is the end of section 1.8. I hope this helped.